Right, so we'll start now. So in the last lecture was the lecture 19, right?
20.
Oh, that was 20, sorry. So in the previous lecture, we discussed the modified equation. So the first thing I talked about was a truncation error. So once you have the modified equation, you can correctly find the order of the truncation error. So in this case, it was order delta t delta x, but you could have some cancellation happening because of the equation the equation has both x and t terms. So because of the cancellation, you can get higher order truncation error. So for that, you need to write the modified equation to correctly find or characterize the truncation error. Next was stability. So we saw that through some physical or numerical ideas, we were able to identify the CFL criteria for this equation. But if you have another equation, you can find the stability criteria for that as well. Right. The next thing we talked about was the general nature of the error, as to how the error looks like or how the error behaves, depending on the nature of the discrete equation you have. So if we have a first order upwind equation or the kind of those equations we have, you'll see the right hand side will have a diffusive leading error term. So the coefficient of the leading error term will be second order gradient of phi with respect to x. So that is like a diffusion term. So that is the equation number A that you see here. And on the other hand, although we didn't discuss it, but if you have a second order upwind, then you end up getting a higher order scheme. So the first or the leading error term we have on the right hand side is the third order derivative of phi, because modified equation has first order derivative of phi with respect to x and so on. So in this, I mean, the second order, third order, and so on. So on the right hand side, the first error term will be, or leading error term will be phi xxx. Okay. So these two equations have a very different, or a very their behavior of the error, the solution, sorry, is very different. So we want to characterize that. So we started with equation number, if we started with the exact equation. So in the exact equation, if you write it as a Fourier series, you can write it as this boxed equation that you have phi exact. On the other hand, if you follow the same process for the first order upwind modified equation, you get phi numerical, which is the second boxed equation. And we see, when we compare these, we see that in the second or the numerical case, the amplitude decays exponentially. That is purely because of a numerical reason. There's nothing physical about this decay. Because in the exact solution, the top one, the top boxed equation, we see that it is summation over amplitudes times the exponential e to the j something. So e to the j something is simply sine and cosine, right? They're oscillating terms. So a naught k, which could be anything, but in this case, in the numerical case, we have an a naught k multiplied by an e to the power of minus alpha k square t, which is e to the power of a positive number times t, a minus positive number times t, so that decays. And that decay is actually proportional to the square of the wave number. So waves which have a higher wave number, which change faster in space, or if you had the time coordinate instead of space, you could call it a frequency. So if the waves which have a higher wave number tend to decay faster. So what that would mean is that if I had a solution which looks like the one on the top, which as a Fourier series, you can see it has two frequencies or two wave numbers here. One is a large wave number, one is a small wave number, which is this first one, and the other one is a large wave number, which is a strongly oscillating function. So when you superpose them, then you get the one on the top, which is the solution. This is just an example. Okay, you could have many different wave numbers dominating in any solution. So here what will happen is, if you use a numerical first order upwind scheme to solve this, you won't get the actual solution. You will get only the first part of the solution, because the second part will decay very fast because it has a very large wave number k. Okay. So what the first order upwind schemes do is, because of the presence of that diffusion term on the right hand side, they will tend to smoothen out the solution. So smoothen means that those fast wiggles that you have on the solution will tend to decay, so it will become more smooth. So these kind of errors are called amplitude errors. So we'll continue with that discussion today. Well, I wrote the same thing twice. So let's say we had a solution. The exact solution looked like this. It was a discontinuous function. And in 1D wave equation, what you see is that the solution gets transported with a certain speed. So what happens is you have some initial condition. The exact solution will look exactly the same, except that it will move somewhere else. It's like you have flow happening, and because of that, the hot water or the cold to hot water interface will simply move from here to there because of the flow. So more hot water is coming, so it's all cold here. So what you'll see after some time is that the interface between, or the step between the hot and cold interface will have moved to a further distance. Right? So this is typically the behavior of wave equation or 1D wave equation. So this is how the exact solution will look. You'll just say transported somewhere else. Whereas if you were to use your first order upwind scheme, then because of this amplitude error, now what is a step? If you write a Fourier series, it will have infinite number of k values, and all of them will have contribution. Okay, that's what a step is. So you can think of a step as a limiting case of something with a very large wave number. So it has contributions from large wave numbers as well. So when you use a first order upwind scheme, what happens is the large wave numbers will die, only the small ones will remain. So wave numbers are like this. So you have a small wave number, then you have a slightly larger wave number, then you have even larger, then you have even larger, and so on. So they all contribute together. If you write the Fourier series, which is not that difficult, you can see that all of them are contributing. But when we use these amplitude errors, what happens when we have these amplitude errors, the large ones will start decaying. So what you will get is Well, near the step, otherwise it's the function is mostly constant. So there's no oscillating term in the Fourier series. So what you see is that till some point you have this constant, but near the step, it was supposed to be a step, but it actually becomes smooth. Something like this. Right. So whenever we see this behavior where the sharp points get smoother, you can clearly figure out that this is because of amplitude errors or because of the first order upprint scheme. And these errors are also called dissipative errors. And this is typical for first order schemes.
So, but when we consider more number of terms in Fourier series, then this numerical solution can be differential solution.
If you are writing the exact Fourier series, yes. But what happens is, as we saw right now, that the higher wave number amplitudes will start decaying. Just like you are removing higher wave numbers. So if you remove them, then only lower wave numbers are retained. Okay, so in that case, you see a smooth solution because smooth solution basically is attributing to your lower wave numbers.
So we can't get the exact solution from the numerical.
But if you have amplitude errors, then if you write the Fourier series, okay, the exact solution, and that will show you a step. But now what you do is you remove the higher wave numbers. So this the quick oscillations will be removed, and that is what the smooth solution. So you cannot get the exact solution because you have amplitude errors. If you did not have amplitude errors, yes, you could get it, but that's the problem here. Okay. Now we may be dealing with an exact solution with an exact equation, which actually has a diffusion term in it. Now we are expanding beyond one kind of equation. So let's say we have an equation which looks like del phi by del t plus u del phi by del x, but on the right hand side we also have a diffusion term which is because of some physical phenomena. So this is the actual equation we are trying to solve, let us say. And that can very much be true because we have this equation called the convection diffusion equation, which demonstrates a lot of physical processes. So let us say this is the exact equation we are trying to solve, and we are using a first order scheme. So if you use a first order scheme, so with first order scheme, the modified equation, can anyone guess how the modified equation will look like for this equation with the first order scheme? So what will we have on the right hand side? It's a first order scheme. So we'll have, we already have this term. That's the exact equation, but when you write the modified equation, you get phi xx times alpha as well. That alpha is coming from your numerical scheme. So what happens is you actually end up getting a coefficient added to b. B is because of the physics of the problem, but alpha is because of the numerics of the problem, because we are using a first order scheme. And last time we showed you what that alpha actually looks like, but that's immaterial. What matters is that you have an alpha. So what this is doing is it is increasing the diffusion in the problem, or increasing the dissipation in the problem. By adding a numerical diffusivity alpha. Now it can happen that your alpha actually becomes larger than b, or it becomes of the order of b. And then we get a problem that your numerical diffusion is much larger than physical diffusion. So the solution that we get is sort of absurd in the sense that the actual physical diffusion that we should have had in the problem is now getting dominated by the numerical diffusivity. So the numerical diffusion, because of the scheme of your choice, starts dominating the diffusion term, and hence you get a diffusion which is much larger than what you should have expected. So in this kind of problems where diffusion is actually a part of the problem of the physics, we need some sort of a discretization that does not add an alpha to it. Okay. Particularly, I mean, of course, we would want to have minimize the errors anyways. So we'd want higher order schemes. But here, particularly, I want that because I do not want to. I would want to mimic the physics properly. So I don't want to add some numerical diffusivity into it so that I end up overestimating the diffusion in my problem. Is that clear? So for that, we go to the higher order scheme or a second order scheme. Now remember, this order is because of the powers of delta t and delta x, not because of the derivative on the right hand side. So it's a second order derivative right now, but it's still a first order scheme because order is because this derivative had a coefficient or this derivative was a coefficient of delta t or delta x, as we saw in the modified equation. The second order scheme will give a modified equation which has this kind of a derivative. So it has beta times del 3 phi by del x3. Again, we do the same exercise. We write this phi as a Fourier series. We already know what the exact phi looks like. We can find the phi numerical here by writing phi as just write it as one Fourier term, and then you can write it as a summation. I won't do it. I think we did it for exact. You can do it yourself for this case. So when you substitute this phi into the equation, what you will get is you will get an expression for A, and from there I can write phi numerical as a function of x and t. So A naught, which was the constant, and then we have e to the power of jk times x minus alpha square t, where alpha squared, let's not use alpha, because alpha we use as a coefficient for the diffusion term. Let's call it gamma squared t, where gamma, I'm just writing something as a gamma squared because I want it, because it's a positive number. And let's recall what phi exact looked like. Right? Now this is different. I mean, if we compare this with what we had in the first order scheme, in the first order scheme, the coefficient of the oscillating term e to the power jk was exactly the same. It was x minus ut. The alpha on the right hand side contributed to a decay term in the amplitude. But here the amplitude has not been affected. This time the phase has been affected. So we have e to the power of jk times x minus, instead of x minus ut, we have x minus gamma squared t. So that u term, the speed term, has been modified. U is a wave speed, right? The speed with which the wave is moving. So when you have a second order scheme, what you have is something called a phase error, not an amplitude error. This time the amplitude is not being touched at all. It's the phase that is getting affected, or the wave speed. And what's happening to the wave speed? So instead of u, we have a gamma squared, and this gamma squared is u plus beta times k squared. Okay. Now this beta times k squared could be positive or negative depending on what the beta sign is. Now this time I'm not forcing beta to be positive. But the only effect it has is you can think of a wave moving with a certain speed u. Now if this beta was positive, the wave moves faster. The wave with larger k values will move faster. It's like they start together, a small k and a large k wave, or like we are writing small k on the top. So small k and a large k wave, and as they proceed, the large k wave will start traveling faster, because the speed, the gamma squared, is dependent on beta times k squared. It's a function of k. If beta was negative, then what happens is one is traveling with the speed of u, the other is traveling with the speed of u minus something, so it starts lagging. But what matters here is to identify the fact that they start moving with separate speeds. Now, what is the effect of that? I mean, what is the effect of that? Now let's look at that example that we had, the step. Okay, so this was exact, and if we look at, now this step has many waves, right? So earlier for amplitude errors, what happened was the larger k values were just decaying, so we only were left with the smaller k waves, so the solution became smooth. But this time they are not decaying, amplitudes are not being touched at all. What's happening is they are moving at different speeds. So it may happen that one of them, the larger ones, have moved slightly differently. So what we end up seeing is we see these overshoots and undershoots, because they have the wave has moved to the left or to the right. Solution starts overshooting and undershooting. Okay, the shape of the solution will start changing. You won't see an overall change in amplitudes, but you'll see that if you have a solution with a certain shape, you'll see that now the solution looks different, because this 1D wave equation simply has to transport things, but it's not doing that. It's actually changing the shape, because different shapes, different frequencies or different wave numbers are traveling at different speeds.
How we are saying that the amplitude is not decaying with time?
You just see this phi numerical and phi exact. Amplitude is not changing as compared to the exact solution. So A naught was a constant, right? And this A naught is in the exact solution is also A naught. So if you do the work, you will see that. I have not. So if you to go from this step to this numerical step, earlier we were getting that e to the alpha minus alpha squared alpha times k squared t. So that was showing a quick decay. But here what happens is because of the difference in the order, what you get is the difference, the beta term gets absorbed in the oscillating term. So that's the reason we have this gamma squared, which is a function of beta, has gone into the e to the power of j k term. So that's an oscillating term. There's no effect on amplitude. There's an effect on the frequency or the wave number. Okay, so these kind of terms where the waves travel at different speeds are called phase errors or dispersive errors. Disperse is to spread. You disperse some seeds on the ground. Okay, so here what happens is different waves travel at different speeds. So we call it a dispersive error because they sort of disperse the information around the actual step or around the actual point.
So what is the difference between dispersion and
Dissipation.
diffusion?
No, we are not using diffusion. So diffusion is typically refers to that sort of dissipation and diffusion are used interchangeably. So that dissipation was happening because the amplitudes were dying.
No, I am asking that what is the difference between dispersive and that diffusion?
I'm not using the word diffusion here because diffusion in the literature is used in two different ways. Okay, in this context, but we are using diffusion in the context of dissipation. So you look at this. So we had a diffusive term here, and because of numerical dissipation, we added another alpha to it. So we call it a numerical diffusion term. Okay. So diffusion is when your amplitudes tend to die down because of spreading. But dissipation is simply because they're traveling at different speeds. The amplitudes are not dying. Okay. This wave which had this amplitude just moved somewhere else. But in diffusion, it sort of you'll see that it's dying down amplitude because it's spreading everywhere. Okay. These are just terms. I mean, they have nothing to do with the physical processes that you see. We have to differentiate using some terminology. So we use a terminology dissipation / diffusion and dispersion. Now, in literature, you will see that the word diffusion in this context will sometimes be used. It will say that because the information is being spread either because of lack of amplitude or decrease in amplitude or because of spreading. So we say that numerical diffusion contains two parts. It's either dispersion, it's either dissipation or dispersion. So dissipation plus dispersion collectively is called diffusion in some literature. It's a terminology. In some cases, diffusion is used interchangeably with dissipation. So we will tend to use diffusion and dissipation interchangeably, and dispersion is the other effect because of second order derivatives, second order errors. Or now we generalize that. We'll say that in general, schemes which have first order, or schemes which are first order, or schemes in fact which are odd ordered, they will show dissipation, and even order like second, fourth and so on will show dispersion in the solution. As I said that this is a very important topic, modified equation. You should definitely expect one large problem on this. So please practice the homework problems I've been giving you. So this homework is asking you to write the modified equation for the center time center space scheme for the 1D wave equation. And once you get the modified equation, analyze the truncation error, stability, and the nature of the solution using this modified equation. So these are the three things we have discussed that we can extract from the modified equation: truncation error, stability, and the nature of the solution, whether it's dissipative or dispersive. Any questions? Question? Right. So now we are equipped fully with all the tools and the methods to solve equations for fluid flows. So we have seen that, well, let's write the equation for fluid flows and then start analyzing as to what we know about these equations. So I've written the continuity equation and the x momentum equation. So here your velocity field V has components u, v, and w. That's the unknown. In fluid mechanics, we want to solve for the velocity field and the pressure field. So we want to solve for V as a function of x in t and pressure as a function of x in t. So x vector is simply a position vector. It contains the components x, y, and z. You can write any point in space as x times I plus y times j plus z times k. Okay. So this x vector is simply position and t. You can also write x vector as x comma y comma z comma t. And v vector is simply containing three components u, v, and w. And we are also solving for the scalar field P, which is the pressure field. So if you are able to solve for these four unknowns u, v, w, and p, you have solved the fluid mechanics problem. Equations for fluid mechanics that you have to solve to get this u, v, w, and p are: one is a continuity equation, one is an x momentum equation, the other is a y momentum equation, then we have a z momentum equation. I won't write y and z. All you do is for y you replace this u with a v, this u with a v, and then you get a y del p by del y here, and then again you get this u gets replaced with a p. Similarly for Z momentum equation, you replace wherever you have this V, you replace that with W, and instead of an X in the right hand side derivative of P, you get del P by del Z. Again, any fluid mechanics book will have these equations. I don't want to write them again. We will write those special forms that we'll discuss in the future. But this is what you call these four equations collectively form the Navier Stokes equations. Sometimes it's only the momentum equation that's called Navier Stokes equation, but we'll call this whole set as Navier Stokes equations. So we have four equations, three momentum equation and one continuity equation, and we have four unknowns. So we should be able to solve this system. Now I've written only a special case which is called the Navier Stokes equations for incompressible flow, where you can consider the density to be constant. It does not change with time or space. It's incompressible. You cannot even compress the fluid, so you cannot change its density at all. Okay. For compressible fluids or compressible flow situations, you will see that the equation will look slightly different, especially the continuity equation. It will have a del rho by del T term as well. Okay, but we will only discuss incompressible flow situations in our course. Now, from a fluid mechanics course, you may recall that even fluids such as air, which are highly compressible, you can compress air. You can literally take a box full of air and you can just squeeze the box. It's compressible. But under certain conditions, you can consider this air to be incompressible. Anybody remembers that condition? Now, what is the condition under which you can consider the Mach number is less than 0.3. So if the Mach number is less than 0.3, Mach number is the ratio of the flow speed to the speed of sound in that medium. So if that ratio is less than 0.3, which is quite true. I mean, speed of sound is let's say 330 meters per second. So if your flow speed situation that you're dealing with are less than 110 meters per second, 110 meters per second is a very large speed. So you're dealing with flows where the speeds are less than 110 meters per second, then you can comfortably take that as an incompressible flow situation. So then you can use the same equations for those cases as well. Okay, so that is the reason it makes sense all the more to discuss incompressible flow equation. And the other reason is because that the flow behavior of these two equations are very different. The way we solve them using CFD are very different. It's much difficult to solve the incompressible flow problems rather than the compressible flow problems. Compressible flow problems are straightforward. So from a CFD point of view, it makes sense to deal with the more challenging equation. So we'll discuss the incompressible flow equation in this course. Okay. But there is an issue. I mean, you can see the x momentum equation, and you see that it is sort of like the equation that the common form that we had. The common form was del phi by del t so we have a del u by del t. Then we have to go and recall this. So we had a u dot grad of phi. And here we have a u dot grad of u. But this that's okay because we are transporting the x momentum here. So we get a u. In the y momentum equation, you get a v instead of phi. So phi can be replaced with u, v and w and you get different equations. On the right hand side, we have a pressure term. Let's forget that. And then we have a diffusion term. It's very similar, isn't it? And this term you can call a source term if you want to. It is exactly the same as what the common form was. So you replace phi with a u, you get x momentum equation. You replace phi with a v, you get y momentum, and you get replace phi with a w, you get z momentum equation.
It should be v dot del phi instead of u dot del.
Okay. So yeah, I'm writing the velocity field as v this time. Okay. So we have three equations for three transport of u, v, and w. But what about pressure? There is no explicit equation for pressure. The fourth equation or the continuity equation is simply a compatibility equation for the velocity components. It says that three components you find, they should collectively be compatible with this equation. They cannot be arbitrary. the x, y, and the u, v, and w components of the velocity v vector cannot be arbitrary. If you find two, the third one has to be compatible with this condition. It's called continuity or the compatibility equation for u, v, and w. So there's no explicit equation for pressure. So that is where the problem occurs, that we have to figure out how to get pressure out of it. So based on that, different methods have been developed. Okay, so in the future, in the next 1 month that we have remaining, we'll discuss these different ways to deal with the pressure in these equations so that we can solve for u, v, w, and p together. In the next lecture, which is on Thursday, we'll start with the technique called the vorticity and stream function formulation. So I urge you to please recall what vorticity and stream function are. I'll also send you a link of a video where it's discussed, so some video lecture in fluid mechanics. So if you do not want to open the book, you can go through those video lectures. It's an undergraduate level lecture where you can recall what vorticity and stream functions look like. Okay, and then we'll formulate the equations using them and solve them, and we'll have a lab after that to show you actual fluid mechanics solvers that you will be writing yourself using the ideas you've learned till now. Okay, thank you.